Alright, good morning everybody, welcome. So we thought today we'd show you a couple of the Geographics LogM products and sort of how they might be integrated into your workflows. Here are the goals. I'd like to show you a couple of the key capabilities of these tools and how they integrate with the rest of the geophysics tools in Geographics. We'll build a fluid substitution AVO workflow, and then we'll talk a bit about implications for unconventional plays. I realize not everybody's working directly on traditional AVO, but that's no reason that this particular presentation wouldn't be of interest. So we'll start with actually driving the fluid substitution workflow. And then I'll do a simple stratigraphic and structural modeling demo. And we'll talk about the fracture detection workflow and then do overall questions and answers. So without further ado, let's go to the AVO demo.
Morning, my name is Ren. Gonna show the AVO demo. So first, we're gonna start with the fluid substitution. We start with open well. We start with the Texas gas. Now we have 3 wells shown. To do the fluid substitution, we go to first tools, fluid substitution. We're gonna have a fluid substitution wizard. First step, we want to estimate the gas. So first we click on the toggle this one, and we want to calculate all the depths, not particularly area. So we choose from 0 to 12600. The program will adjust these parameters automatically. All the rest parameters are pretty good. So
we're going through here and basically running the model assuming 100% water saturation here. And then we'll actually substitute gas in the gas zone to create the AVO model.
We go to next. Default parameters also good. Next step now, and the last step is also not bad. So then we're done. Now we get 2 other calculated curves. One is Seismic Institute. We click on the space area, the curve will pop out. Another is the porosity new. Now we get these 2 curves. We want to adjust the scales of the Seismic Institute. To do that, there are 2 ways. One way is right-click on the name. Then we get the log scale. Choose a log scale. Left and right, we change to 800 to 100. Click OK. Now we have modified Seismic Institute. Next step, we're going to calculate the curves with a substitution of 20% wet,
80% gas.
So to do that, first we copy the curves. Copy all the curves beside sonic gamma ray. Done. We click the space area. Okay. Okay. Next, we do the same as previous tool, fluid substitution. This time, instead of insert 100% wet, we toggle it off. And we want to give it to the specific area, which is within these two areas. So there are two ways. One, we can directly enter the value, or we can click the area of interest. So, example, we go to here, and depth we choose to here.
So top and bottom of the gas zone in this case.
It's all good. We accept all the default parameters. We go to next step. This time, instead of 100% wet, we go to gas, and water saturation change to 20%. We can also change the parameters of the temperature and pressure. In this case, they are all good. We accept the default parameters and go to next. These are all good. Next. So now we want to update our curves. We toggled.
Yeah, I should probably say one of the good things I feel about this tool is the defaults generally are pretty good. So even like a naive or junior user of the tool can run the workflows and sort of count on sensible help and actually pretty good warnings too if you do something wrong. So that's I feel one of the nice things about the tool.
Okay, now we update curves to the new created curve and toggle these three to the also those new curves. We're done, we finish, click OK. Now we get extra porosity curve. Only for the interesting zoom. Okay, one more step we can do is we can click and drop curve. Now we overlap curve, the same curves with different properties. So do the same for the others. Now we can compare these curves. Okay.
Very nice.
Now we're done with the fluid substitution. Any questions? Okay, we're good. Now I'm going to the next step of the AVO simulation. To do the AVO simulation, first step is we have to change into the time mode, and in edit we have to do the time alignment. These default parameters are good. Click on apply. And
so what just happened there, folks? Obviously the sonic, well, all the curves start where the logging started. So naturally the assumption is that time 0 is where the logging started. So again, we're saved by pretty good default. What happens if you don't have better velocity correction via check shot or something, the tool will straight line velocity from the top of the log to datum between the initial log value and the replacement velocity at the surface. So thus we have a start time of whatever, 4.65 seconds instead of 0. And that's obviously important to get the angles right for the AVO.
Okay. After we finish this step, next step we go to AVO. It's in synthetic. The second AVO, AVA. So we're gonna calculate two AV sections. One is for the gas zoom, another is for the fluid substituted with 20% wet. Initially, this one all looks good. We can change the offset, the minimum offset stack. We can change the maximum offset. In this case, just for demo, we can change the maximum change the maximum offset to 12,000 and 3 stacks divided to 0 to 4,000, 4,000 to 8,000, and 8,000 to 12,000. Then we accept all those default parameters and click OK. And click on the space area, we get the simulated AVO. One thing, another way to view these synthetics is in File, Plot. We'll edit Plot View. Now we get this. We can zoom in to the seismic traces. Now we can see the seismic traces with the gas.
Okay, so obviously the plot view is useful for those of you who, well, make presentation quality paper stuff still.
Next, we want to compare the AVO with the fluid substitution. So we can choose the sonic and the density log to the new calculated and change the parameters, the maximum offset the same to the previous one we did, so that we can compare them side by side.
Yeah, Rand didn't do it, but you can save those defaults if you have a sort of typical prospect default you like.
Click on OK. We get a warning. The reason is every time when we calculate the AVO, it only left one AVO section on this software. So when we click OK, it would overwrite the gas AVO with the fluid substituted AVO. So in order to compare this side by side, we can also still go to the plot. And now we have the left is the gas AVO compared with the right, the AVO with the fluid substitute.
So we can see there isn't a tremendous AVO response in this case, but a really nice bright spot, very typical Gulf Coast sort of answer, I guess.
Any questions? Okay. Now we're done with the AVO fluid substitution section. Now I'm going to handle this one to Barry.
Thank you. Okay, so as I said, I'm going to do a just a really simple stratigraphic and structural model demo here. We'll start with the model builder. Whoop. I'm just going to select the same well twice, so we'll have absolute simplest possible model here. All right. And I don't need the synthetics in this case, so we'll get rid of them. And I'm just going to zoom in. Oh, wait a minute. Let's see here. Let's add some tops. And again, this is a Gulf Coast example, and yes, the default correlations will delete any existing ones, of which there were none. Now I'm just going to zoom. Let's see. All right, so my story for the demo anyway is we've got a slightly shalier section you can see from the gamma ray here, and the play is what would happen if there were a channel incised into that. So I'm going to add a couple of new correlations called top shale or top shaly or something like that. And let's see, how about I'm sure you guys are convinced by now that you're not going to hire me as an actual geologist, which is okay. And I'll add another correlation called bottom shale. And we'll pick that, I think, maybe at the base here. Yeah, how about there? Okay. And just for visuals, we're going to define body lithology and color it in, basically. So here's what I'm calling the shaly zone. And for contrast, we'll color above and below sandy colored. Save this as, I don't know, 5 or something. Certainly not in Canada. That'll do. Okay. And exit. And then we'll go into the structural model builder. Import the cross-section that I just built, which is right there. And fine for defaults. Let's boost the number of horizontal samples just for fun. And there's my cross-section model that I just created. So let's zoom in on the zone of interest. How about, I don't know, there. And then I'm just going to create my hypothetical incised channel here. And this is pretty simple. You can just draw it, basically. Something like that. Okay. And current body is channel. Whoop. Pattern I can leave white. Velocity from previously squinting at the well logs, I would say for sandier areas about 10,150 at this depth. And you see you get a default density, which we can go with. right, and then I'm going to save it. And yes, trace models associated obviously will be changed. Of course, there weren't any. Now I'm going to go to synthetics. And I'm going to create an image ray synthetic on this model. And you can see Ricker wavelet, 26 hertz. Let's do a couple hundred traces. Go. All right, so here's my synthetic. Let me zoom in on the ray trace just for a jiff. Okay, so we see the lensing effect of the incised channel. And on the synthetic response side, let me turn off the body fills so we can see the wiggles a bit better. All right, so there we have it. Slight amplitude effect, but a definite time delay associated with the again, hypothetical channel that I put in. So that's the end of the modeling demo. Do we have any questions there? Let me go back to the slide deck. Whoop. All right. So you say, but I'm not working in the Gulf of Mexico. I'm doing unconventional shales. And I say to you, basically it's the same. Couple of papers that I'd like to bring to your attention. First was by my buddy Andreas Ruger from Landmark when he was doing his PhD with Ilya Tsonkin. Sort of a classic paper. And essentially the notion here is when you are perpendicular to the direction of maximum stress, you get exactly the same sort of VPVS ratio changes with offset that you do in conventional AVO work. So the modeling essentially all applies. And the second paper is a little more in detail. It's in geophysics, but again, you know, it's Ilya and students. And these are both well worth a read, I think. So yeah, changes in VPVS, like I said, and of course, depending on whether you have gas or liquid fill in the fractures, exactly the same again as conventional AVO. So in this case, I'm not going to take you through the actual demo, but what I've got here is a model. This is from the Niobrara, and what I've done is altered the shear sonic response, actually pretty conservatively. So you can see the two shear sonics side by side. I hope you can see my mouse pointer. So the fracture sonic simulates velocity change that would happen if we had a more highly fractured zone in the Niobrara. And we see the response in the synthetics on the right. And I'm going to go to the next slide so we can look side by side. In this case, more so than the actual NMO-corrected synthetics, I think the most diagnostic is the stacks. So you can see the top of the Niobrara, this sort of trough, doesn't vary too much with offset, but in the fracture simulated case, we have pretty much identical near offset response. But look at the far offset response. We've essentially lost that trough almost in its entirety. So if you're working with your processor and you know your stress orientation, or maybe even if you don't, some gathers by offset and azimuth, either just for comparison or perhaps subtracted to generate an attribute, would be quite diagnostic of more highly fractured zones in the Niobrara. All right, I think that's the end of that. Call to action. We'd love you to test drive these things if you don't have them already. I strongly believe that these are good tools, and they'll give you a lot more insight into your plays. Being able to model what ifs, being able to model actual rock properties that you know about. Come and see us at the SEG convention. I'll be there. Morgan will be there. Come try out the tools. And of course, there's the website.